So in this clip I'm going to talk a little bit about constraint forces. These are probably the hardest thing for people to wrap their brains around because of the fact that they don't, there aren't sort of nice mathematical expressions for constraint forces. Rather, constraint forces actually are whatever they need to be in order to make things work out. And in this clip, what my intention is to try to just give some examples of constraint forces and show how they change depending on what the situation is, so you can think about what it means for something to be a constraint force. Later, when we start to talk about solving equations of motion, you'll see how constraint forces sort of drop out in your solution. All right. So probably the classic example of a constraint force, so there are certainly other kinds of examples, is a normal force. Okay? And the, sort of physically what the normal force is that force that keeps some object from falling into or from being pushed into another object. So let's say I've got, some block and I've got maybe some, interesting surface, and I push this block and it sort of slides along the surface, right? And so it goes down here and then it comes back, and it's moving along, and this surface is holding it up. Well, if you ask the question, why is the surface holding it up? At a microscopic level, it's because microscopically you have these two interfaces, you have atoms in both of the materials, and the atoms don't want to be too close to each other, so there's an electromagnetic force that pushes that object up. Now, you're used to seeing this sort of expression that, okay, here's a block, it's sitting on the ground. That means that there's a gravitational force, mg, and there's a normal force. The normal force is equal to plus mg j hat. The gravitational force is equal to minus mg j hat. Okay? And so often people say the normal force is kind of the opposite of mg. Not true. It does turn out to be that case often, but it is not by definition opposite of mg. And one sort of simple example that you can think of that says that's not true is, what if I have this block that's sitting on a table, but I come along and I push down on the block, right? So I'm pushing the block down. Now at this point, I'm applying a force to the block, right? So there's me pushing down on the block. Gravity is also pulling down on the block. And the table is pushing back up on the block with some normal force. Now the table is going to push back however hard it needs to in order to keep this block from going into the table, because I'm not nearly strong enough to actually make the block overlap with the table. So the harder I push, the bigger that normal force is going to be. And in particular, that normal force will be whatever the magnitude is that I'm pushing on it with, plus mg in the j hat direction, assuming that the gravitational force and f me are both down. And so this is a pretty simple case where it says actually the normal force is not simply the gravitational force. You can also see the block is exerting a normal force on my hand, right? I'm pushing on the block with f me. The block must be pushing back on me with an equal and opposite force. Okay, so that's one example of how it is that normal force is not necessarily mg. Let's think about another example, though, and it relates to this sort of idea that I've got a block that's sliding along some surface. Well, what's the normal force at different points along the surface? If I think about the block, say, moving at a constant speed along the surface, you can see that at this point, for example, there must be an acceleration that the block is exerting, right? Because the block's velocity is changing from being horizontal to being a little bit up. That means at this point there's an acceleration that is up. Okay? In order for there to be an acceleration up, there's got to be a net force on the block that's pointing in that direction. And the only interactions that are present in this case are gravity is pulling down on the block and the normal force is pushing up on the block. So at this particular instant here, if the block is moving, the normal force is going to be greater than mg, because you need to have both the normal force to counteract gravity and an additional normal force that's pushing it up. Similarly, at this point, if the block is moving over this hill, you can imagine the normal force has to be less than mg, because now the net acceleration is down, and so that means the normal force must be less than the gravitational force at this point. So the normal force will take whatever value it needs to in order to keep the object from falling into the surface. It's worth thinking a little bit about some special cases of that, like what about this case? Let's say I've got a block that's moving at a pretty big velocity, and it gets to this point where there's this really rapid drop-off. Well, what's going to happen in that case? I think you know what the answer is to what's going to happen. It's actually going to fly off, right? It's not going to follow this. And why will it fly off? Well, it'll fly off because at some point you're actually asking the block to, if the block were to follow this, that path requires a downward acceleration. And in particular, you could imagine this block might require a downward acceleration that's greater than minus mgj hat, right? So it actually, in order to stay on this track, the acceleration necessary would be downward, and it would be bigger than mg. But if you think about it, the normal force can only push up in this case, right? The normal force can only be normal to the track and upwards. That is, it can only keep the object from going into the track. It doesn't keep the object from flying off of the track. And so in general, for a sort of surface, the normal force is as big as it needs to be, but it can only be in the positive n hat direction, which is to say the normal force for this case where you've got an object sitting on another surface, the normal force is only allowed to point upwards, right, to push the object, to keep the object from going into the track. It's not allowed to pull downwards. It's not allowed to be in the minus n hat direction.